In condensed matter physics, today we are going to start a very important chapter, and this is actually free electron theory of metals. Okay? This free electron theory of metals is a very important chapter of solid state physics, and it is the study of this chapter is necessary for all the students of solid state physics of all levels. In spite of that, you are a student or you are a university student or you are preparing for any competitive examination, this chapter is equally important for you. Okay? So this is our first lecture on the free electron theory of metals. As it is our first lecture, so actually in this first lecture, we will only see a brief introduction of this chapter. That is, what is this free electron theory of metals and how this theory was progressed. We will just give a brief account of it. Okay? And after this brief introduction, in the second video, we will start the real concept. Okay? So let us see some introductory fact regarding this free electron theory of metals. And as I have told you that the free electron theory of metals is a fundamental model, or you can say a basic model of solid state physics. And this theory actually describes the behavior of electrons in metallic solids. Okay? So this is called free electron theory of metals. Okay? In fact, this theory was at first devised by a famous scientist named Drude in 1900. Okay? The theory proposed by Drude, which is called free electron gas model or free electron theory of metals, was redefined or refined, you can say, by a famous scientist Sommerfeld in 1928. Actually, Drude theory is purely a classical theory, and in Drude theory we will see later on that electrons are treated as a classical particle. Okay? But you know, electrons are actually not classical particle, but electrons are actually quantum particle. Okay? So Drude theory has so many limitations because its assumption that electrons are classical particle obeying the classical mechanics, that is Newton's laws of motion and the Maxwellian distribution law. These assumptions are not actually 100% valid for electron. So this Drude model, which was proposed in 1900 by Drude, this was later on redefined by Sommerfeld. And in Sommerfeld's theory, you will see that actually the electrons are treated like a quantum particle. Okay? In fact, what we study in free electron theory of metals, as it is a theory of metals, so definitely this theory must support or must explain the important physical properties of metals. The two very important properties of metals are its electrical conductivity and its thermal conductivity. You know, electricity can flow through the metals, heat also flows through the metals. So this electrical and thermal properties of metals are explained by the theory of free electron theory of metals. Okay? In fact, the thermal properties of metals are also explained along with the electrical properties. And while explaining these properties in this theory, the electrons within the metal are treated like a gas-free particles. It means the system of electrons inside the metal treated like a gas. The metal surface acts like a container, and the electrons behaves just like the molecules of a perfect gas. This is actually the basic idea of Drude theory, in which the electrons were just compared with the gas molecules, and the equations which are valid, which are obeyed by the molecules of perfect gas, that were actually utilized for dealing with the motion of electron in Drude theory. Okay? Now we will see in very short, in very brief, the important concept, or you can say the key concept of this chapter. As you know, the chapter is free electron theory of metals. So definitely a question has been raised in your mind. When you say free electron, what does it mean? Here actually free means free from force. Free from force. As you know, in a metal, in the atom of a metal, there are two types of electrons. Let us suppose this is the nucleus, and the extra nuclear electrons are revolving in these orbits. Okay? You know that the last orbit of an atom is called valence orbit, and the electron present in the valence orbit, or the outermost shell you can say, is called valence electron. Since the distance of this valence electron is large from the nucleus in comparison to the distance of electrons situated in the inner shells. Okay? So the Coulombian attraction on this valence electron is much smaller in comparison to the electrons in the innermost shell. And that's why you can say that the electrons in the valence shell are loosely bonded to the nucleus. Not completely free, loosely bonded. If you are talking about an isolated atom, the electron in the outermost shell remains attached to the atom. It does not escape the atom. But what happens in case of a metal piece? So if you consider that this is a metallic specimen, and you know in this metallic specimen there will be a large number of atoms, and each atom has electrons, and the valence electrons which are loosely bonded to the nucleus, if you will consider a metallic specimen, then the valence electrons are completely detached from the atoms. These are detached from the atoms, and they move freely inside this metallic surface. Have you understand or not? Let us say there is an atom containing Z electrons and Z protons. Z is the atomic number, and let us say that this X is the number of valence electrons. Number of valence electrons. Okay? So in the case of a specimen, the atom loses this X electron, and those electrons move randomly inside the metallic surface. Actually, metallic surface acts like just a barrier. The electron does not escape through the barrier at a normal temperature, but all those valence electrons moves freely inside the metallic surface. Those electrons are actually called free electrons. Why it is called free? Yeah, now you have to understand. These electrons just behaves like the molecules of a gas which contained in a container where they are in random motion. So I have mentioned it here that this theory assumes the valence electrons of the metal atoms are not bonded to the individual atoms, but are free to move throughout entire the metal. Have you understand? And these free electrons are responsible for conduction of electricity, and that's why these are also called conduction electrons. Okay. In fact, what happens, as I have told you, that if you consider that there are Z electrons, then in the nucleus there will be Z protons, and so nuclear charge will be plus Ze. And if our atom loses X electron, that is the valence electrons are now detached from the atom, then what will happen? Let us say A is your atom, and this atom actually acquires a positive charge, let us say plus Q, and electrons has been released. This is actually the minus Q. This is charge of the electron. Okay. So if in fact number of valence electron is X, then this Q will be equal to X into E, where E is the electronic charge. Okay. And so the atom now loses its valence electrons, which are free to move inside the metal, and the atom becomes ions, positive ions. Okay. So in this way, inside the metallic specimen, there is an arrangement of metallic ions, positive ions, and the electrons are moving, electrons means valence electrons are moving randomly in that positively charged background. And those electrons are called actually free electrons. Okay? In fact, in this theory, a model has been proposed initially. This is called electron gas model. Electron gas model. Actually, the free electrons in a metal are modeled as a gas of non-interacting particles moving randomly within the metallic lattice. The positive ions that make up the lattice are considered fixed, providing a uniform positive background and balances the negative charge of the electrons. I have just explained it. You can see that after the detachment of the valence electrons from the metallic atoms, there will be positively charged inside the metallic surface, and in this the negatively charged this dot represents actually the electrons, and these electrons move randomly. Its motion is in fact random. Okay. But the total charge of the positively charged ions and the total charge of the negatively charged electrons are equal in magnitude but opposite in sign. So if you will measure the net charge, that will be equal to 0. Since the electrons are moving randomly inside the metal surface, because these electrons do not experience any force in accordance with the classical assumption. Okay? Because in this classical theory of classical free electron theory, it is assumed that the electrons are a non-interacting particle. No two electrons interact one another, that there is no interaction between the electron and the ion, although it is not very correct, because you know electrons are negatively charged particles, so there must be at least a Coulombian interaction between them, and there will be also Coulombian interaction at least between the ions and the electrons. But in the classical Drude theory, it has been assumed that these interactions do not take place. So the electrons are treated as non-interacting particles, just like the molecules of a perfect gas are non-interacting. Okay? And that's why you will see later on that in a classical theory, that is classical theory, or you can say in Drude model, we assume that electrons have no potential energy. It will have only translational kinetic energy due to its random motion. Okay. Now, in fact, what I am talking, just that is called classical Drude model. Okay, classical Drude model. Actually, the Drude model, which is the earliest form of free electron theory, treats the electron as classical particles, and these classical particles obey Newton's laws of motion and the Maxwell-Boltzmann distribution law. Okay, so these particles do not obey Fermi-Dirac statistics. These particles do not obey Bose-Einstein statistics, but they obey Maxwell-Boltzmann statistics in accordance with the classical Drude theory. But at present quantum mechanically, actually electrons are fermions. They obey Fermi-Dirac statistics, not Maxwell-Boltzmann. But in Drude model, it has been assumed that electrons are just like a molecule of a perfect gas, and so they are governed by Maxwell-Boltzmann distribution law or Maxwell-Boltzmann statistics. Okay. Actually, we will learn in very detail in our first lecture on Drude model. In this introduction, I am just giving you a very brief insight of these things. But in detail, we will learn about Drude model or Drude free electron theory of metals in our first lecture, in our first conceptual lectures. Okay. In fact, you will learn that this Drude model, according to this Drude model, if this is a specimen of a metal, okay, then electrons are moving in this specimen in random direction. But it means motion of the electron is random, and so that the net charge flowing through any section of this specimen will be zero, because the probability of moving of charge from left to right and right to left will be same, and that's why you can say that the net amount of charge flowing through any section is always zero. And as net amount of charge flowing through a section is zero, so you can say no electric current will be constituted. Okay. But what will happen when we connect this specimen by a battery? In other words, you can say when a voltage or a potential difference is established between the two ends of this specimen, then what will happen? When the voltage is applied between the section A and B, then an electric field will be produced, which is directed from higher potential to lower potential, that is from A to B. This is the direction of electric field. And due to this electric field, the free electrons experience actually the electric force. If E is the electric force, then what will be this? F will be equal to minus E into E. And due to this force, the randomness of motion of the electron will cease, and the electrons will start drifting with almost uniform velocity in opposite direction of the applied field. And in that condition, there will be a net flow of charge through a section of the metal. And as a net charge passes through a section of the specimen, so electric current will be constituted. I will be not zero. So how electric current is constituted what is the mechanism, all these things can be explained by the classical Drude model. But we will learn about these things in very detail in our next lecture. Here I am just introducing you. Okay. Again, this Drude theory also gives the, or you can say that this model also explains actually the Ohm's law. You know, Ohm's law, according to Ohm's law, the electric current is proportional to the applied voltage or the potential difference, I proportional to V. This can be explained by Drude model. You will see in my next lecture. I am just introducing it here, but the explanation will be in next lecture. Okay. Apart from that, when we will learn about the drift velocity in terms of Drude model, then you will learn how the electrical conductivity sigma can be explained. So Drude model also explains the electrical conductivity of metals. Okay? Electrical conductivity of metals can also be explained by Drude model. Okay? But as I have told you that this classical Drude model is based on the assumption that electrons are non-interacting particle, which is wrong. It is not correct. Electrons obey the Maxwell-Boltzmann distribution law. It is also incorrect. Actually, electrons obey Fermi-Dirac statistics because these are fermions, half-spin particles. And so there are so many limitations of this Drude model. What are those limitations? All these things we will discuss in very detail in our first lecture. Okay? But after this Drude model, Sommerfeld modified this theory and introduced the quantum theory of free electron theory of metals. Okay? Quantum theory. So this is called Sommerfeld's quantum refinement. Okay? In fact, this Drude model's major limitation, as I have told you, was its reliance on the classical mechanics. Sommerfeld improved this by incorporating quantum mechanics, specifically Pauli's exclusion principle and Fermi-Dirac statistics into the free electron model. Okay? Because electrons are fermions, and you know fermions obey the Pauli's exclusion principle. So taking the Pauli's exclusion principle and a spin of electron under account, Sommerfeld developed the quantum theory of free electron theory of metals. Okay? In fact, according to Sommerfeld's theory, the electrons are treated as quantum particles and their energies are quantized. This quantization of energy leads to the concept of Fermi energy. In this chapter, in our forthcoming videos, you will see a very detailed explanation of this Fermi energy. But for the time being, if you want to know in one sentence what is Fermi energy, can you say? Actually, Fermi energy is the highest energy of electrons in a metal at 0 Kelvin. At absolute zero temperature, what is the maximum energy of electron in a metallic specimen? That maximum energy of electron in a metallic specimen at 0 Kelvin temperature is called Fermi energy. And this Fermi energy will be explained in very detail in our forthcoming lecture. Okay? And you can also see this explanation in my videos on statistical mechanics in Fermi-Dirac statistics, where you will find a great explanation on this Fermi energy. Okay? Actually, if you consider that this is your specimen, then electrons are, and this specimen is at 0 Kelvin temperature, that is at absolute zero. The electrons in this metallic specimen are actually lying in different energy levels. You can see these lines which I have drawn here represent the different energy levels. And let us say this AB, is the highest energy level up to which the electrons are occupied. But above this level AB, the electronic energy states are empty. It means there are no electron above this energy level AB. Then this AB is called Fermi energy level, and the energy corresponding to this energy level, which is denoted generally by EF, that is called Fermi energy. So in simple way you can say that Fermi energy is what? The Fermi level or Fermi energy is the highest energy occupied by the electrons in a metallic specimen at absolute zero temperature. Okay? So in this way you can define this Fermi energy. Okay? In fact, the electrons occupy states up to Fermi energy, and only those near the energy level contribute to the electrical and thermal conductivity. In fact, the electrons, let us say the electrons lying in this energy level, this is far apart from this Fermi level. These electrons are inner electrons. These do not contribute to the electrical and thermal conductivity. But the electrons lying in an energy level close to the Fermi energy level, that take part in thermal conduction and electrical conduction. Okay. Now, in free electron model, a very important concept you will discuss in our forthcoming lecture. That is called the concept of Fermi surfaces. Actually, what is this Fermi surfaces? Actually, the concept of this Fermi surfaces is very critical, very crucial. Okay? And this idea of Fermi surface has been introduced in Sommerfeld's model. Actually, this Fermi surface is defined in momentum space. So it has been mentioned it here. You can see it is a surface in momentum space. That is a space which is formed by momentum. Instead of x, y, z coordinate, you have to take px, py, pz as the coordinates. And such a space is called momentum space. And this Fermi surface is defined in momentum space. Actually, this is the surface which separates the occupied states from the non-occupied state or unoccupied state of the electron at 0 Kelvin temperature. As you can see, I have shown it here that if this is the Fermi level, this is your FL means Fermi level, and all these states are actually occupied, which I have darkened it here. These are completely filled states, or you can say that these states are occupied completely by electron, and the energy states above these are empty. It means there is no electron present in this. So this occupied state and this empty state is separated by the Fermi level, and a surface on which this Fermi level lies, that is a surface in momentum space which separates the occupied states of the electron and the unoccupied state of the electron at 0 Kelvin temperature. That very surface is called Fermi surface. But this is not all about the Fermi surface. As I have told you in the beginning of my lecture, this is just an introduction. So I am just introducing you to the different terms used in this chapter. But we will learn about this Fermi surface in a complete 50 minutes video in our forthcoming lecture. So the subject matter of Fermi surface is very important for you, and that will be dealt in very detail in our forthcoming lecture. Okay. Actually, this Fermi surface, the behavior of the electron near the Fermi surface determines many properties of the metals. And those properties are actually electrical conductivity, heat capacity, magnetic susceptibility, and so on. These are some important properties that can be explained, that can be determined by considering the electrons near the Fermi surface under account. Okay? And considering those electrons which are near the Fermi surface, one can easily discuss and explain the electrical conductivity, heat capacity, magnetic susceptibility of a metal. Okay? So these are some the basic facts regarding this free electron theory of metals. But as I have told you earlier in the beginning of my lecture, that this theory is this theory has so many limitations. Okay? Because in this theory, electrons are treated like a free particle, although electrons will be not completely free. Definitely electrons cannot escape through the surface of the metal. It means there is some potential which prohibits it. So electrons which you say free electrons that are not actually completely free. Okay? And as you know that in this theory, it has been assumed that electrons are free particles and non-interacting particles. But as electrons are microparticles having negative charge, so there must be at least Coulombian interaction between the two electrons. Two electrons must repel one another by electrostatic force. There may be other interaction too, but at least Coulombian interaction must take place between two electrons. And apart from that, as you know, in this theory it is assumed that the electrons are moving in a background of positively charged ions. But in this theory, it is assumed that there is no interaction between the electrons and the ions. It is also wrong. It is not possible that electrons which are negatively charged particle will move in a positively charged background, but there will be no interaction. It is not possible. So the neglect of electron-electron interaction and electron-ion interaction, this is not very true. It is not true. So definitely in case of a true theory, these interactions must be taken into account. So I have mentioned it here that the theory assumes that electrons do not interact with each other or with ions in the lattice, which is not entirely accurate. Okay? So this is its first limitation. Now this theory, the second limitation of this theory is that it does not talk about band structure in solid. Actually, our solid had band structure. In fact, you will learn about this band model of solid in our second chapter. After the completion of free electron theory of metals, we will start the concept of band theory of solids. And then you will see that actually inside a solid, bands are formed. But the free electron model does not talk about this band model. But band model is a physical reality. Okay? So the theory does not consider band structure of solid, which is crucial for understanding the behavior of electrons in materials other than simple metals. Actually, in the physics of simple metals can be explained almost correctly by free electron theory of metals. But if your aim is to discuss the physics of semiconductor, okay? If you want to discuss the physics of superconductor, you cannot explain it by the concept of free electron theory of metals. Okay? So for this we say that since this theory does not give an idea of band formation in a solid, so this is it's one of the drawback. Okay? Now there are so many phenomena in solid state physics that cannot be explained by this free electron theory of metals. So you can say that inadequate explaining all phenomena. You can talk about the phenomena like superconductivity. If you want to explain superconductivity or magnetic properties and behavior of semiconductor by the free electron theory of metals, you cannot succeed. It means the explanation of superconductivity, magnetic properties and properties of semiconductor cannot be explained by the use of free electron theory of metals. Actually, these properties can be used, these properties can be explained in terms of band theory of solids. Okay? But you can see that the free electron theory of metals laid the foundation for more sophisticated models, such as the nearly free electron model and the band theory of solids. Despite these limitations, it remains fundamental concept in the study of solid state physics, providing essential insights into the behavior of conduction electrons in metals. Okay? So these were some important facts regarding the free electron theory of metals, and I hope you have definitely now have been introduced about the free electron theory of metals. And as I have told you earlier, that in our forthcoming lecture we will see the actual theory, actual concept of this free electron theory of metal. We will start from the Drude theory or Drude classical theory, and after that we will start Sommerfeld's theory. Okay? Thank you very much.